Let me introduce myself. I used to work at Google. I then ran my startup FutureCam. I then worked as CTO of a different startup. I now work as a part-time CTO with multiple companies at once. Today we are going to discuss design patterns. Design patterns are like templates. A same problem has been encountered again and again. Someone came up with a solution and they wanted to share it with the rest of us. And a name is given just for reference. Doesn't mean you need to do it that way. It's a pattern, it's not a rule. And there are patterns for other things as well. For example, you may be in the habit of, I don't know, ordering your lunch from Swiggy and then going for a shower. Maybe that's your habit, let's say. That doesn't mean you need to do it that way. It's just a pattern. You can do it the other way around if that works better. So don't think of patterns as rigid, as rules, like this is how you must do it. It's not like you must get a security check done before you board an airplane. It's not a rule of that kind. It's a pattern. It's like, hey, if you have this problem, the solution may help. May help. Sometimes it makes things worse. Sometimes a different way may work better. So with that general understanding in mind, let's look at design patterns. The first one is lazy initialization, which is very commonly used nowadays. In Swift, and I'm going to refer to Swift for this project, but the principles apply to all stacks, all platforms. In Swift, you have this lazy keyword that does it for you. So this is initialized only when you access this, like this code is run. In this case, it's not much, but if it is a lot, this matters. If your language doesn't offer this, the older way is just to check on all access, whether it is nil. And of course, you can have a helper function. So suppose this wasn't there. This would be the more traditional way of implementing this. So the lazy keyword is just a syntactic sugar. And you can have lazy local variables as well. So if you have a function like this, let a equal to something, let b equal to something, let c equal to something. And let's say this code has multiple branches here. And A, B, and C are not all accessed in all parts. Then you can, let's say B is lazy, B is very expensive to initialize. You can do this. So then here, let's say you're using B. Here you're not using B. Then only in this case B will get created. So it applies to local variables as well, the lazy keyword. Singletons are also lazy in modern programming languages like Swift and Java, especially in Swift. This is created only when it is used. In Java, a class is initialized as a whole when it is loaded. So it's still lazy, but not lazy to the level of individual members of the class. Unlike C, C++, where global variables are initialized before main runs. So that has a whole set of problems. However, in modern languages, typically you don't need to worry about it. Moving on. Future Cam is a camera app, and in a camera app, you tap to focus, right? We had a bug where sometimes the focus square that comes on screen, the focus rectangle, you'd get two of them on screen at the same time. So how did I solve that? I made it a singleton. And this is an example of using a design pattern to solve a problem. The problem is you want to have only one focus rect on screen. And there's a design pattern for that. So it's a fit, right? Don't force fit things. Use things when they naturally fit into what you need. Because this is shared, and in a singleton you have a public shared variable like this, and the initializers are all private. This even gives an error. Never mind that, but this one. So it can be used only by the same class. There is a variant of it which I call a singleton at once. This is a class that can have only one instance at a given time. So you create one, you use it for a while, and if you create a second one concurrently, the initializer checks that it is nil. And if it is nil, you'll get an exception saying that it already exists. So you can't have two concurrent instances. But after the first instance is deallocated, you can have a second. And if you look at the variable, it's weak. So it doesn't prevent the variable from getting deallocated. And in Java, you would use a weak reference again. So in this case, analytics data is used to record analytics data for a capture like a video. So let's say you're recording a video. When you start recording, an analytics data object is created to track analytics regarding the video. How long was it recorded? Was it recorded in day or night? All these factors. And when you stop recording, the analytics data is sent to Firebase. And that's it. The object is thrown away. If after a few minutes you record another video, a fresh object is created. So this is a use case where it's not a singleton because you don't want the previous analytics data being mixed with the current one. Each capture is different, each analytics object is new. You just can't have two objects at the same time. And you can't access this variable because it is private. So this is what I call a singleton at once. And because the current variable is private, somebody has to hand you a reference to this class. You can't just directly access it. This lets you control access to the object because with a traditional singleton, one of the complaints against it is it's a global variable. Everyone can access it. You lose control because you have a certain layering in mind. You have a certain set of modules and you have an idea in your mind which module should talk to which module and so on. All this layering goes out of the window with singletons because they are global variables, as with any global variables, right? So you don't want that to happen. You want to control access. So anyway, this is a singleton at once. This is the name I came up with. And you can make up your own design patterns, right? Design patterns are not handed down to us from the heavens. Come up with your own. They're just patterns. Somebody like you came up with the patterns we use today, right? Make up your own. As long as they meet your requirements and they're clearly defined, independent of your application's logic, it qualifies as a design pattern. Moving on, I also have an access controlled singleton. I don't know if I have an example in this code base. I don't think I do. An access controlled singleton is a different version. What it does is you can have only one instance of the object throughout the lifetime of the program. It's like a traditional singleton. You don't create it, destroy it, recreate it like a singleton at once. There's only one object. But this is still private. So somebody again has to hand you a reference to this. So that is a access controlled singleton. Moving on. Another design pattern is a wrapper. This class, non-real-time video writer, it finally writes a video to the disk, creates a video file. You can then play it, you can then save it to your gallery, you can upload it to a server, you can do whatever you want, but this class writes a video file to the disk. It's implemented using the iOS API for this, which is called AV Asset Writer. It's a wrapper. So you have one class that wraps another class. And the wrapped class is not exposed. That's a wrapper class. And it offers things that are logical for its abstraction, not the underlying abstraction. For example, this has a frame rate. Let's say the frame rate is 60 FPS. Irrespective of the rate at which you save, so basically you create this non-real-time writer, you give it a frame rate when initializing it, and then whenever you want to add a frame to the video, right? A video just consists of frames that play one after another. Whenever you have a new frame, you call append frame. And then you call stop recording and save. And by the way, this is good naming because it already tells you what it does. So this is how you use this class. You instantiate it, you append frame, append frame, append frame. Once you're done, you say stop. So now, irrespective of the rate at which I call this function, each second of the video will have so many frames. So let's say it's a 60 FPS video. Now, I am able to append frames at, I don't know, 6 frames per second, let's say. That means the video will play 6 times faster than the capture rate. So normally in a video, you capture frames at a certain rate and you play them back at the same rate. So the video runs in real time. This is a non-real time video writer. It doesn't care how fast or slow you are capturing. It just cares about its frame rate. So if you're capturing 120 a second, the video gets, so assume the frame rate is 60. Now if you're capturing 120 per second, the video is slowed down. If you're capturing 6 per second, the video is sped up to match this frame rate. This is the abstraction of this class, and it automatically takes care of the timestamps to make that happen. Whereas the underlying API lets you create any kind of a video file, real time, non-real time, anything. But a wrapper doesn't expose all the functionality of the underlying class. It exposes the functionality that is needed. Moving on, let's discuss an adapter. What does an adapter do? It adapts a class to a different API. Here the class being adapted is a metadata tracker. It has a certain API. We need it to support this API. That is where the adapter comes in. It just invokes the underlying API, converting some arguments as necessary, converting the result back as necessary. Right? And in this case, the conversions are just casts. But you could do different things, right? You could imagine converting the exposure duration from a double to a string, or whatever it is, right? You could imagine filling in missing data in this dictionary or map with default values. An adapter can do anything. It's no different from I don't know, like a USB adapter, right? Like a dongle. It adapts something to something else. The difference between a wrapper and an adapter is with an adapter, you have a class that has the wrong API for your use case. The wrapper is not about that. A wrapper is you're implementing some functionality and you have an underlying class, which is just an implementation detail. Moving on. The next design pattern is something I came up with. This is what I call a unifier. This is the video. I'll leave a link in the description. With a unifier, you have two different classes and you want to unify their APIs. These are two different classes built by two different people, maybe in two different times. For example, one class in this example is from 2010, another is from 2018 or something, 2016. So they're like years apart. They have different capabilities, different APIs, but you want to unify them to a certain extent. So that in the rest of your program, you don't need to have if cases. If the object is instance of this, handle it this way, else handle it that way. You don't need to do that, right? That's a unifier. You can say it's a variant of an adapter. With an adapter, you have an A and you need a B. So you're adapting the A into a B. With a unifier, you have A and B, and you don't really care about the direction of unification. A can be made to look like B, B can be made to look like A, but finally you have one thing that works for both. Moving on. The next pattern is an immutable class. In a camera app, you have a rule of thirds grid. You see this? Including future cam. That is what the preview overlay is. And this is an immutable class. There are no properties in it. There are no callbacks. There are no getters. There are no setters. There's nothing to modify. You just create a preview overlay and add it to your UI. An immutable class is one that cannot change its state. And this is a tool to use when appropriate, as with all tools. And the advantage of this tool is it really simplifies usage. I never have to worry about this class. It's there. It has been added to the UI and it just works. It doesn't interact with anything else. I don't need to worry about have I configured it correctly? Have I initialized it at the right time? Does this depend on something else? When that class changes its state, does this redraw itself? I don't need to worry about all of those, right? Thread safety. All of these concerns are generally eliminated with an immutable class. And in fact, some programming languages like Haskell rely on that. And there are people who say that's a better programming model. So when you take any of these design patterns, entire languages have been designed around them, making them the central part of the language, as with immutability in Haskell. But you don't need to go so far. You don't need to use Haskell. You can use it as a tool when it is appropriate in your existing programming language. And there are a few things to take care of when you define immutable classes. All the variables should be final and let, not var. The class itself should be final so that someone can't override it and make it mutable. And all the parameters to the initializer should make defensive copies so that they're not modified later on. Deep copies, and all these things are there. So anyway, moving on. The next design pattern is an IIFE, immediately invoked function expression. This is an example. You're creating this variable. You have a function. It's an unnamed function. It is invoked, and the return value is used to assign this this variable. So there are two things here. So there's a local variable which is used temporarily during the process of initialization. The advantage of this pattern is nobody sees an uninitialized variable. You could have alternately built it this way. And then in initializer or your constructor, you can do all this. Let's do it in the real constructor instead of doing it here. Let's look at the diffs to see what we have done. Oh, I haven't saved it, I guess. All right. So we have a traditional variable here without using an IIFE, and we are initializing it this way. Do you see the problem here? Before we initialize it, a reference to self is being sent to some other class, which might very well access the video data output and see the uninitialized video data output. This is the problem that IIFE solves. With an IIFE, it's already initialized by the time you access it. There's no way to access an uninitialized value. Moving on. The next pattern is called a chain of responsibility. It's where multiple classes work together to achieve something. So one class does a little bit of work, then invokes the next one, which does a little bit more work, then invokes the next one. Let's look at an example. In this class or protocol, AV capture photo or CM sample buffer, you have a save function. It checks what kind of instance this is. So there are two instances of this, as the name says. One is AV capture photo, one is CM sample buffer. And what save does is, it checks which type it is, and it dedicates to an inner type. So if it's an AV capture photo, if it's not an AV capture photo, it is a CM sample buffer. And then you access the underlying pixel buffer of this. and then you save. So here, CM sample buffer is delegating to pixel buffer, which is delegating to a CG image, which is actually creating a graphics context and drawing into it and saving it to the photo library. So this is a chain of responsibility. Moving on. The next design pattern is a helper class. And we all know this. We may not even recognize this as a design pattern. And that's because some of these design patterns have become so common. Singleton, lazy, IIFE, etc. Let's look at permission requester. This class's job is to request permission. So you see the prompt when you use an app, right? Can this app use your camera or photos or microphone? Can this app send you notifications? All these permissions are requested in one place. And the reason you would have a class like this is one is to declutter the other classes, which are too big already. The other reason is you want to enforce some logic regarding this. So in this case, you want to request permissions one at a time using callbacks. So what it does is it invokes one, and then when it returns, it invokes the second. When it returns, it invokes the third. Except that one of the iOS APIs for location access is buggy. Sometimes it never invokes its callback. So that is at the end of the chain, so that even if it doesn't return, the app doesn't hang. And the reason one at a time is otherwise, if you invoke concurrently, iOS has a bad UX. It shows one dialog box, can this app access your camera? And before you can say yes or no, the dialog box disappears and a second dialog box appears. Can this app access your photos? And then when you say yes or no, it disappears and the first dialog box reappears. And it's not even an overlay, like one dialog box coming on top of another. There's an animation. The first one disappears, then you go back to the app for a fraction of a second, then the second one appears. It's a bad UX. And since it's the first experience with the app, we don't want that. So that's what this takes care of. So by having a helper class, you're able to take care of some of these things. Moving on. The other design pattern is an observer. For example, the zoom level property of the camera, you can observe it. And whenever it changes, you get a callback. Here. This is used to update the zoom button. You're observing this, and whenever it changes, this callback is invoked. And it updates the zoom button by showing the exact value. So if it changes from 1x to 2x, the button says 2x. Right? So this is a way of decoupling things. The camera doesn't need to know what someone is going to do when the zoom level changes. It just knows there's an observer, I need to invoke the observer. Another design pattern is pub/sub. So here, when the user unlocks all features by paying for the app, this notification in iOS peak, it's not a notification like in the UX sense, right? You get a notification from an app. It's not that kind of notification. iOS notification means a pub sub really. So this pub sub is posted and anyone can listen to it by using its name. So this is how you post it, and this is how you observe it. This dot observe. And you can do whatever it is that you want to do. So for example, we have a lock emoji to indicate that some screens in our app are locked. And we add or remove this whenever the payment status changes. So you can do whatever you want. The person who is posting it does not need to know who is listening or what they do. This is different from the observer, where to observe you need to have a reference to the object. If you go back here, to observe the zoom level, you have to have a reference to the camera. In a pub sub, you don't have to have a reference to the IAP controller, which is the one that is posting. You just observe based on the name, which is just a string. So this is further decoupled. Is that good? Is that bad? It's bad more often than it is good because it leads to spaghetti code. It does have a purpose. The purpose is that multiple people can post it and you can receive it in one place. The receiver doesn't even need to know if there's one or multiple posters. The problem is, whatever layering you're trying to set up in your app can be easy to violate because everyone is randomly using this to cut through the hierarchy and talk to whoever they want to talk to. So in fact, we had many more notifications in or pub subs in FutureCam. I got rid of all of them except this. If you have one, see if it makes sense. One way to see if it makes sense is to get rid of it. And if you find yourself adding a lot of forwarding functions, where the IIP controller, instead of posting this notification, invokes some class, let's say the main controller, saying payment status changed, which invokes something else, saying payment status changed, which invokes something else, which invokes something else, which eventually invokes the code that needs to run. If you have these kind of forwarding functions that don't add value, then perhaps using PubSub is cleaner. Otherwise, don't use PubSub. So that's a way of figuring out whether PubSub actually helps or not. And ultimately, all these design patterns, they're not about theory, they're about practice. If you implement a design pattern and it makes your code worse, undo it. I worked with an engineer who said every class needs to have a factory. No, every class does not need to have a factory. A factory is a tool for a specific problem. If you have that problem, you need to use a factory. And after using it, you need to check that the code has actually improved. Compare the diffs before and after. Is it actually solving a problem you have? Otherwise, revert it. The proof of the pudding is in the eating, or whatever the saying is, right? You can cook whatever you want, but finally, if it's not tasty, you've cooked bad. Similarly, you can use whatever design patterns you want, but unless it improves the code, revert them. Moving on. The next design pattern is a template method. A template method is when you have a class that defines a set of high-level steps or actions. But some of these actions can be customized by subclasses. So let's look at mode. In a camera app, you have different modes, right? Long exposure, time lapse, video, photo, etc. They are all instances of mode. And it has a bunch of high level features or things, right? It has a user description, which is a string that appears in the UI. It has a locked, unlocked status. It is informed when the shutter button is pressed or released. Now, some of these can be customized by subclasses. So if you look at time lapse mode, when the shutter button is pressed, it can decide to do something. So this is a template method. Don't confuse it with templates in C++ or generics, where you have a list of employee or something. It has nothing to do with that. It's just a sequence of high-level steps or some high-level things, some of which can be overridden by subclasses. And the others which don't need to be modified, don't need to be overridden. So you could have Different classes overriding different methods. And some of the methods may not be overridden by any subclass at all. Some of them may be overridden by all subclasses. Moving on, the next design pattern is the state pattern. The state pattern applies when you have a class that needs to behave differently in different situations. For example, if you take let's look at it from the UX point of view. If you take a camera app and if you press the shutter button, what should happen? The answer is it depends on the mode. If you are in the photo mode, it should just take one photo. If you're in the video mode, it should start recording. And when you press it again, it should stop recording. Excuse me. Whereas in the photo mode, the second tap has no special meaning. It just takes a second photo. It's not a start stop. They are two different photos. Whereas a burst mode, when you press the button and hold it down, it may start recording a burst. When you release it, it may stop recording a burst. You can see how the app behaves differently in different modes. Now you have this mode hierarchy, which we already saw, which is the template method pattern we discussed a minute back. But now we are discussing the state pattern. The purpose of the state pattern is to have a class hierarchy of modes and you have a current mode variable in the outer class like camera. So originally when I implemented the app, I tried to put all the functionality in camera. But since there are different modes and it needs to behave differently, it was not a workable solution. So then I created this modes hierarchy and I have a variable here that captures the current mode. And the camera delegates certain actions to the mode, which are dependent on the mode. This is a state pattern. When you have a class that behaves differently in different cases, create a class hierarchy, then create an outer class like camera in this example that delegates functionality that needs to change based on the mode to the mode class and implements functionality that doesn't need to change itself. Moving on, another design pattern is an asynchronous method where you have a function. It does not have a return type, but it invokes a callback. You may not even think of this as a design pattern because it's become so common. Moving on, the next design pattern is a facade. A facade is a class that encapsulates multiple subsystems. In this case, a camera, it encapsulates multiple iOS subsystems. You have AV capture for capture. You have core image, CI image. It is for GPU accelerated image processing. You have PH photo library. This is for saving to the gallery. And within AV capture, you have video related stuff, video capture. And then you have audio capture from the microphone. All of these subsystems are encapsulated by the camera class. You don't need to know all these things. So that's a facade. So anyway, these are some design patterns I wanted to walk you through with concrete examples. If you'd like me to work with your team, there's a link in the description.